All right, good morning. Welcome to week 9, our second last week together. So what's happening this week? Well, as usual, we have a weekly test that came out last week and it's due Thursday, so please don't forget to do that. We have more labs to help you get your head around the concepts of linked lists, trying to do interesting things with linked lists. Conceptually, these are the most difficult labs of the course. This is the hardest concepts. Deleting and manipulating linked lists are the hardest things we have to work with. I guess the other big thing that's happening right now is assignment 2. So hopefully you've taken my advice and have already started assignment 2. Wouldn't be panicking if you haven't made a lot of progress, but you should have made a big step towards getting your head around what you have to do and made at least your first steps on assignment 2. It's an interesting assignment in that you're given a lot of code there, so there's a lot you've got to look at, a lot you've got to think about, and it will take time. Now, this is not wasted effort. All right, so you get an internship, or after you leave UNSW, you probably won't be writing code that works with Pokemon and Pokedexes. That's true, but we've chosen this assignment because it's a model. It's a simpler model of exactly the sort of code you are likely to be working with. So if you get an internship, you're likely to be presented with exactly this sort of thing. What it'll be doing will be less boring, less fun than Pokemon, but it'll be exactly the same sort of tasks. There'll be existing functions that do this, do that, manipulate this sort of object, and you have to create more code that manipulates these objects to do things you want using the methods provided. So the skills you develop in assignment 2, learning how to read an specification, read existing code, and a big part, by the way, of reading the code you're given is not reading it line by line and trying to grasp every last semicolon. It's trying to scan through, understand what you can. Don't get too frustrated if there are little bits in there you don't understand. Try and get the big picture, understand the important stuff. By all means, put a question in the forum. What does it mean to use an assert here? And Shrey or someone else will tell you, oh, you don't need to worry about that, but here's what it does. Or they might say, oh no, that's incredibly important. The asserts, by the way, not incredibly important. We haven't had a chance to talk about assert. We might see if we can fit that into the next lecture, but it's not important for the assignment at all. So that's the assignment. Yeah, as I've said, try and work on it continually. Put in, set aside an hour tonight, an hour tomorrow night, whatever, and then don't pencil in 12 hours this weekend. I'm going to do the assignment in one go. Now, sure, if you've done a couple of years of C coding, yeah, that's a perfectly reasonable thing to do, but you haven't, have you? So you've got to give yourself time to work on this. And the other phenomenon I'd talk, maybe it's already familiar to you, but it certainly happens to me and everyone I talk to, is you work on these things and you get stuck at some page, and you'll go away and do other things, and you'll be eating dinner, standing in a shower, going for a walk, and it will click with you that something you had to fix, and you go back, and the problem you had been thinking about for hours, you'll solve in 5 minutes. All right, that's assignment 2. Well, I guess the other thing we should remind you is we're all online here. Sydney is locked down. Everyone's talking as though lockdown's going to. We're still. It's starting to look optimistic that we'll be back for T3, but your estimate is as good as mine. Let me repeat my advice to you. There's a huge, confusing array of information about COVID-19 coming out, exposure sites, what you're meant to do, and so on. You're exactly the sort of person who's well placed to comprehend this sort of stuff, where things are happening. And please try and help your family and friends keep safe by, if you think they might have been to Campsie Woolworths on this day, let them know. You can scan this stuff, get through it quickly. You're incredibly online. Maybe your family and friends aren't. So, yeah, use your skills to help everyone get through this. All right. And yeah, I guess a shout out to all those people who I know many of us are stuck in households with family, and that's so much easier. If you happen to be caught in Sydney alone, I really do feel for you, and reach out to student support services. You know, you're an international student, you don't know anyone, and COVID's left you unable to do anything, just locked at home. If you're not coping, reach out to UNSW support services. All right. Right. What are we doing today? Now, we're going to recap what we did in the last lecture first, and we're going to follow on to that to something called abstract data types. And it integrates nicely with our work on linked lists. I'm going to show you an abstract data type, and I'm going to implement it with a linked list and then with an array. Show you both, but I'm going to show you how the example we did in the last couple of lectures to show you linked lists in Battle Royale, how that relates to how it can be considered sort of an abstract data type, and we'll work through from there. So hopefully this will flow smoothly through. But first, let's recap where we are with... Oh, I should mention help sessions as well. We've got help sessions running. I don't honestly know the details, but you can ask in the forum if you can't figure out when they're on, but they're linked to the class homepage anyway. Or ask in the chat if you want to know about help sessions. So we do provide help, particularly for the assignment. That's where students really need it. And we schedule extra help sessions coming into the assignment due date just for that reason. Now. All right. Oh, actually, I dumped this function. I rewrote this code afterwards. I thought this wasn't very good code, and I actually dumped this function. There we go. Let's make sure I'm telling the truth. So I simplified my code a bit later after the lecture. Come on. There we go. VLab. Does it all? Oh, yeah, it all compiles. All right. So we wrote some functions. Yeah, and I just want to look at what the functions we wrote were. It was all for a game, but we wrote functions that manipulated a list of players. Now, what were the functions we wrote? One, to create a player. Now, the only information we stored about players was their name. You can imagine you might want to store more information. Why would you imagine that? Well, the assignment. The assignment's exactly this. You store Pokemon properties. But that's sort of classic sort of thing. You probably have multiple pieces of information to store about an object. It raises all sorts of interesting information, by the way. You're storing information about sets of objects. And we have a wonderful databases course with the code COMP1511, I think, which everyone who wants to study computing should do. Apologies to you mechanical engineers and so on, you probably can't fit it in your program, but if you're a computing major or in a dual degree, you certainly want to take that course. So create a player with a name and saying who's the next player in the list. Print players, print all the players in the list. Insert a player in alphabetical order in the list. Remove a player by name from the list. And we had two functions. Yeah. So already I'm seeing that I'm coming back to my code and thinking, oh, this is not very good, Andrew. Why am I thinking this is not very good? It's style. It's naming. Naming is the most important part of style. Well, perhaps it's the hardest important part of style. There are things, I guess, yeah, all right. Indenting is more important, and indenting's easier. We all figure out indenting sooner or later. And there are other, but choosing good names. So why am I saying I'm looking at these functions, and I should be able to look at the name of each function and know what it does. That's not always possible, and often there's extra information, ancillary information I can supply by comments. But remove that player, remove by name. Well, they remove, but what's the difference? Ugh. Now, one reads a name from standard input and removes that player. So it's probably the remove by name. That should be really read player and remove. Can I fix that? I don't see any reason why I can't fix that right now. I thought I'd make the point I'm trying to make. Alright, can I work gedit to replace functions? Thoughts and prayers here. Come and do COMP1511 with me and I'll show you lots of better ways to do these sort of things. So remove by name. I'm suggesting a better name for would be read name and remove. Alright, thoughts and prayers. When you're doing this sort of thing, please have backups. Or you could learn how to use a software repository. COMP1511 would be the first place that we cover that. Ooh. That's a bit better. And insert alpha. It really should be, well, let me fix that as well. What's a better name for insert alpha? That's okay. Oh, it makes it a bit long. Long function names are generally good. Yeah, that's nice. Some better names there. Hopefully that still compiles. Let's go down and look at how we implemented these functions. I'm going to break up this file shortly and move main out of there. Alright, so that's our main function that inserts 6 players and then lets us delete them one by one until we have a winner. That was great. Let's remind ourselves of what that did and how. Who's just been, oh, I've changed it a bit. That's okay. Chicken's just been knocked out. Bye bye chicken, bye bye Zoe, bye bye Mark, bye bye Tom, and bye bye Shrey, and Anusha's the winner. So that's it all in action. How do we code that up? Yeah, what else do I want to recap here? Yeah, there are a few things I wanted to highlight. Right, when we're creating a player, the player name is an array. We could put a for loop there to copy the array. That would be fine. But the array is a char terminated, sorry, a 0 terminated char array, and strucopy, a helpful function, saves it a few lines of code and does the copying for us. And it's easier to read. When you've done a lot of C programming, you've seen a lot of strucopy calls, you see that call, think, ah, I know what that does. Print players goes down our list and prints each item. Right, so hopefully you look at that and think, ah, I know what that does. That's obvious. You're getting on top of doing things with linked lists. This is the classic loop that does one thing for everything in a linked list. The harder operations are changing the list, inserting, deleting, or where we have several lists and we want to do, is this item in both lists? Is this item in one list? And so on. That gets interesting when we nest loops. And yes, you get to practice this in the labs. Right, this is our insert player alphabetically code, and this is hard. So this is the tricky sort of code I'm talking about. That works down the list to find, oh, alphabetical order. We manage alphabetical order using the function strucomp, short for string compare, by comparing the name we're looking for to the name in the list, and if it's alphabetically after our name, we stop. Now we've got a programming problem in that what we're really interested in is the list item one before the one that's after us alphabetically. We can't go backwards in a list. Pointers go one way in a list, so we can't go backwards. But so we used a nice little programming technique here, programming trick. We had an extra variable which we always had tracking the last thing we're at. So we have one pointer pointing to the list item we're working on now, and one tracking to the one before. And every time around the loop we say, keep track of the one we're at, now move on to the next. So it's tracking one behind us. And we use that previous pointer then to tack that in the list. Now, if you haven't, if you can't, you need to understand this code. I'm not saying it's easy, but you need to understand this, inserting this. Do diagrams. There are diagrams in the lecture slides for the previous lecture, but work this out yourself. Make sure you understand this code. It's hard but important. So that puts the player in the list in alphabetical order. So we finished up, and you can see the alphabetical order over here: Anusha, Mark, Shrey, Tom, Zoe. So if we added another player, using this, they'd get inserted in the right spot in the list. Right. So, and probably in the wrong order, there's code that reads a name and removes it from the list. This gets rid of the new line out of the code. Yeah. So fgets gives us a line of input with the new line. The only time you won't get the new line is if input runs out before any new line is ever supplied, or the array overflows without a new line. And this is sort of a bit paranoid, saying if I got a new line, remove it. And then it says remove the player of that name. So this isn't conceptually that hard. This code's a bit weird, and this code I don't like. It has one issue here: the fgets never checks the fgets works. So really robust code would check here with an if statement saying, did the fgets work? How do we know if fgets works? It returns null if it failed to read anything at all. It's not important for what we're working on, but really solid code would always check that an fgets work before going on. And this is the code to delete a player from the list. So it says, I'm looking for a player of this name, delete them from the list. Same issue, we need to delete a player from the list, we need to change the pointer to that player, which is in the previous list node. So we've got this same programming technique where, I don't like the abbreviated variable names. We've got a pointer we're moving down the list, cur, short for current. Why do we have to save those 3 letters? I'm not sure. And this is, but programmers do this endlessly. They go back and look at their old code and think, oh, I could have fixed this, or they waste time. And you tell a programmer to do something, and they say, did you add the 3 new features? And they say, no, but I went back over my old code, and it's so much more beautiful now. Don't be that programmer. I guess you can write beautiful code to start, of course. It's not a bad idea. Actually, yeah, that's sort of a yes and no thing. Your task may be to clean out code. So often, you might get an internship or something like that, and your manager will just say, well, look, first task, this code, I really need to, checked, maybe reworked a bit, documented, tested. So you might go through and make the code pretty, add some tests, add some documentation. Be a second person or third person or an extra pair of eyes that goes over code. All right. So if you're with the extra pair of eyes, you might be changing these variable names to be more readable. But the crucial thing for us, I'm getting a little sidetracked, sorry. The crucial thing for us is understanding these concepts here. This deleting an item from the list, what it's doing. And that crucially depends on getting this pointer pointing at the previous node in the list. And it's working through a few cases. One possibility is we never found the player in the list. So that's our first possibility. We asked to remove someone from the list who's not there. I can show you that in operation. So I can say remove Andrew from the list, and Andrew's not in the list. So that in that case, we'd get to the end of the list and cur would be null. The next possibility is if you knock out the first player in the list, which if I can type properly and spell Anusha's name properly, there. In which case, if we're knocking out the first player in the list, the previous pointer will be null, in which case we change the head of the list to point to the next item in the list. So when we knocked out Anusha, we're setting head to be head next, the next field in Anusha, which would be chicken. the other possibility is we're removing this a second, third, fourth, fifth, sixth, an item further down the list, which we do just by pulling them out of the list like that. And we always free up space. Alright, that's my code recap there. Let's keep moving on. What now? Alright, I wanted to restructure this code a bit. So these functions here, they look sort of useful. They look like they could be used for a few things. So I'd like to package them up separately in a file and make them available for multiple purposes, possibly used in multiple programs that want to manipulate a list of players. Maybe I'm going to invent a series of games or whatever. How would I do that? How would I break these up into separate files? Let's first create a main.c, and I'll create a main.c and put main there. So I'm going to work through this just to show you what happens so you understand the mechanics. Make sure we're all across the mechanics here. Let's clear that. Alright, so I want to take main out of this. So my plan is to have battle royale.c that's got all these really useful functions in one file, and then we can have multiple programs that couple a different main with these functions and use these functions. Delete main.c and put it over here. And I'll do the usual hash includes to.h, and are we good to go? Now I expect you know what's going to happen. If I say to C, say to DCC, here's main.c and here's battle royale.c, compile them together. It's saying, look, Andrew, there's all these function calls in main.c and I don't know what the hell they are. You're calling insert player alphabetically. Now, you being a normal person might think, well, wait, why doesn't DCC look in battle royale.c and figure out, you know, this call in main.c is in battle royale.c? And it's a good question. It's a good question, and there are reasons, bad reasons, not so bad reasons, good reasons that C doesn't do this. But in the end, it is what it is. You've got to accept it. C compiles each file separately, and we can use this for good things, and we can minimize the extra work it creates. How do we do this? I'm going to show you both in this lecture. I would say there are many possibilities here by the way with computing language. Now, what we're going to do, of course, is create an include file. So main.c needs to know about these functions, as does Battle Royale. If we have information we need in two files, we put it in an include file. So let me create an include file, which we'll call battle royale.h, but let me, sorry, I'm embarrassed by my lack of gedit proficiency here. Alright, so we've copied that there. Oh look, gedit isn't syntax highlighting it because it doesn't know what it is. Interesting. And we'll call that battle royale.h. Alright, so I've got all these shared information that has to be in two files. No actual code. Remember, that's one of our rules. Never put an actual function in a .h file. So you'll never see curly brackets, printf, hello, something like that. All you see is a declaration saying there's a function called free players that has one argument of this type and returns nothing. So you don't, but you never actually see the actual code for free players in a .h file. With that, I can now, in both files, so hash include battle royale.h. Note the different angle brackets, the weird angle brackets for a system file, double quotes for our own file in the current directory. All right. And I can do that here. And there. Now we'll compile. Yay, and work. All right. So that's how we split a program into multiple files. Now, more. I want to do more here. The header file, this .h file, essentially becomes the view to the outside world of what's in Battle Royale. So if I've got other people perhaps around the world using my create player, print players, this useful library of functions I've created, then what they know about the functions is essentially in this header file. So it defines an interface. There are two things here, I guess. One is I'd like to use a type def here, and one is I don't like the outside world seeing what's inside a struct player. So why don't I like the outside world seeing what's inside a struct player? It means that, well, what we want to do is limit complexity. We want to make Battle Royale its own little world as much as possible, and have as limited a possible connection to the outside world, so that we can treat it as its own little world and figure it out and get it working and keep it correct. Why? I keep harking back to programs like the Linux kernel, the Linux operating system, 1 million lines of code. How do you manage that sort of complexity? How do you make that correct? I mean, it's running on this system now. It is running incredibly complicated things and working. How do we manage that sort of complexity? It's split up into 55,000 files. And further. There's further divisions of complexity. But if we can isolate pieces, work with them in isolation, get them working in isolation, we can manage complexity. We can also make improvements. So if I want to improve how a part works, if there's a very limited way the rest of the world interacts with it, I can make changes underneath the hood, knowing that they're not going to affect the rest of the world. So it's bad if the rest of the world can see how I implement my player list and then perhaps depend on it. I'd prefer to move this definition out of the include file entirely and put it in Battle Royale. So I'd like to say to the rest of the world, look, yeah, there's a struct player, but I'm not going to tell you what it is. You can create one, you can insert it, you can remove it, you can free it all up. So you can do all these operations, but I'm not going to tell you what it is. So that doesn't stop you doing things with it. And then if I decide, oh, I'm going to change this, I can do it. And I know it won't affect you because you don't know what the internals are. And that will almost work. That will almost work. What's my errors here? problem is here. Alright, save the files. I've still got code here in main that's looking inside what's in a struct player. It's this one. It thinks, oh, I know there's a next field in struct player, and this code here that's printing this out. So what we'd normally do for this is add more functions to rather than say, oh, this code needs to peek inside how we've represented our list of players. We'd give the user extra functions here. So they want to know, they want a function to say, are there any players left? And they want a function to print the player name, say. There are a few possibilities. But let's quickly provide those extra functions to them so that they'd never need to know what's inside a struct player. So we need something that says, returns, I guess, how many players there are in a list. Oh, how would he find out how many players there are in a list? I think there's a print players function. There we go, that will do us nicely. There's a print players function. We can modify that to say how many players there are. You could modify the print players to do that, both of them, print the players and return them. So a how many players function. How do we do this? You're saying it's a nice example, isn't it? We've got this pattern for doing one thing for everything in the list. We copy it and change it to do another task. You might be thinking, oh, couldn't I write a generic routine that was do one thing with a list and supply what the one thing is? You can in C. It's not so easy to do in C. It's not something we can cover in this course, but there are other languages which make sort of focus on that sort of realization and make it much easier. All right, so that counts the number of players in a list. Let's delete the bad comment. You can work out what comments should go there. Actually, no. I can just say that. That's good. What was the other one we wanted? Print winner. Yeah, probably be return winner. Anyway, we'll. I don't want to spend too long, so you could think about what function you want to write here. Yeah, I'm not sure this is a very good choice of. It's poor design, but that'll do. Might compile those. Oh, let me show you a programming trick. Yeah, here's a good one. I just want to check that Battle Royale, which doesn't have a main function anymore, so DCC or complain, I can say to DCC, look, just compile this file and don't worry about the fact it hasn't got a main function, but do tell me about any errors in it. And I've got the type wrong here. Thank you, DCC. See, and before I would have copied this type to the include file incorrectly. Okay. Let's take these, put them in the include file. we added 2 more functions to our interface. I've said the last one's poorly designed, but that's okay. You can work out a better design for that last function. So we've added how many players, print winner, and expose them to anyone who wants to use our wonderful little library of functions manipulating a list of players. Well, that hash define doesn't need to be in. Does it need to be in? Yeah, maybe it does need to be in this file. Yes, it does. Maybe. And now we can need players. And all right. We've removed now all internal knowledge of what's in a struct player, how things are represented from the code that's doing things as a player. So we can write code that calls these functions, plays a game, but never knows what's happening behind the scene. So we can write our code here and think about this, manipulate it, reason about it, debug it. And we can also have these functions over here, and we never have to worry about people calling these functions, looking at these fields. We've kept them private to us. Will all of this work? I don't actually know. Oh, I think it will. We can try it out. Let's get rid of chicken. Ah. Alright. So that's sort of, yeah. Yeah, look at that. So this code interacts with this useful library of functions via these header definitions. I want to take it one step further and hide things a bit more. Yeah, this name length, that really could go back into here now, couldn't it? Not needed in our, we don't need to tell the outside world necessarily about that limit. One thing I'd like to do a bit more type hiding. I'd like to just say there's a type player. Like this. And supply that, tell the outside world, don't even worry about it being a struct. There's just a player type. Let's see if I can change that. So all of those struct player stars become just a player. Ooh, look at that. Yeah, that does make the connection to the outside world a bit obvious. What these functions do more obvious, doesn't? Oh, except oops, that's not so good there. So we're saying to people who want to use my function, yeah, call create player, give it the name of the player and the next player in the list, and it'll give you back a player. Call print players, all you have to do it is the first player in the list. Call insert player alphabetically, give it the first player in the list, and it'll give you back the new first player in the list. Call remove player, and it'll give you back yeah, what does remove get player give back? There really needs to be comments in all of this, doesn't there? So, alright, but let's not focus on that. This change I've just made, don't freak out about it too much. You just saw it's a straight substitution. Anywhere now you see a player, you can replace it in your head by struct player star. But it certainly makes what our functions do clearer, doesn't it? So we're hiding a bit more information from the outside world and making it a bit more obvious what's happening there. Hiding a bit more of the details. Let's make the same change over in main.c. Place all of those. Yeah, it's not perfect. It's still sort of, yeah, this, I don't like to look at this exactly. And it's still retorting the head of the list, and we could do this better. And I'm going to show you how to do a better example of doing all of this. But this is sort of a half step. We've taken this detailed example of this game and split it into two files and put all the useful functions in one file and then use them from a second file, from a main.c. Alright. Both of those examples are all on the class website. Now, you might be saying, yeah, can you really stop the outside world looking in these data structures? In the end, C doesn't allow you to completely stop it. If a C programmer wants to do something, there's always a way they can do it, not good ways. But we're assuming here in a lot of this design it's not, this is not security. We're not setting up walls to stop this happening. We're just hiding the stuff and facilitating sort of, you know, people using these functions in the right way. There are languages where you can actually rely on the information being hidden and inaccessible, I think. Yes, there are. But you should get the picture. I think this will make more sense if we work on to do a completely different sort of object, or set of objects. Let's take a breath. Let's look. I've got some lecture slides here to talk about. Oh, let's go back. Yeah, abstract data types. Yeah, what are they? I'd actually call them a mathematical model. That's the most comfortable way for me to think about them. They're a mathematical model with formally specified operations that do particular things, theoretically specified objects. So they're a theoretical notion. Yeah, I'd say an abstract data type. It's a theoretical notion of something we can write actual code to implement. But because it's a theoretical notion of something, there's multiple ways we can write actual code to implement it. And the theoretical model then lets us tell the world, well, this is what this code does, these are the operations it does, and you can use these operations, but we're not going to tell you what's actually behind them for your and our good. So we can hide the concrete implementation and just tell the world abstractly what these operations are. And this has been found to be enormously useful in software development. This is how we build complex systems that work. We protect data from being accessed the wrong way, and we have this fixed set of operations, and it lets us do really clever things then, like parallelize these operations. Have these operations happen on all 10, 16, 32 cores of a machine. Have these operations happen on 10,000 nodes in a network or in a data center. Spread these operations over a whole continent, because we've got this mathematical model of the operations and we know all the code just does these operations, and we've hidden the implementation. It's really good if you're doing things like this, by the way. You can test them in a tiny data set on one little computer and then deploy it over tens, hundreds or thousands of computers. And this if you're in a computing major, this may be well in your relatively near future. Alright, but let's take baby steps. Our baby steps to it by showing you an abstract data type and how we can work. Oh, there's a spelling mistake there. So one sort of information hiding we talked about was using typedef to give a new type name to something. So we can say there's a type called library, which is really a /struct library star. Note the different case. Because types are such a different thing in C, and we want programmers to be able to read our code and see, that's the name of a type, not the name of a variable, there's usually a convention. Now the convention you've seen for hash defines is all in capital letters, and that's really universal. There's barely a C programmer that doesn't do that. The conventions for type names are less universal, but one common convention, and one we're using here, is I'll stick a capital letter at the start of a type name, just so someone reading it. It's just a convention, but it's a useful one. Alright, so that's typedefs. So what we're going to talk about here is a structure called a stack. We're going to actually implement the what's the word? Analogy, metaphor? No, not. I don't know. We're going to use as a deck of cards, a stack of cards. But the one I always think of is a stack of plates. Now imagine you've got a weekend job in a restaurant when lockdown finishes, and there's a pile of plates waiting to have food put on them. You can only access the top of the top plate from the stack. You can't get at the bottom plates on the stack. There are 50 plates there stacked up. You can only grab the one right on the top and hand that to the chef to prepare the next meal. Similarly, if the person doing the washing up comes in with more plates, they can only go on the top of the stack. In mathematical terms, in theoretical terms, you could think of this as a last in, first out structure. The last plate to be put on the top of the stack is the first one taken out. So the last plate the dishwasher put on the top of the stack is the first one the chef's assistant takes off the plate in the restaurant. So in a stack, only the very top of the stack, the last item to be put in the stack, is accessible. You can't access what's underneath the stack generally. You're saying, why would you have such a data structure? As it's actually really useful. Probably just about the most useful data structure in computing. You've actually seen this data structure in your coding. So C functions are like stacks. When a function's called, it gets functions stack up as they're called. So if main calls function 1 calls function 2, when function 2 returns, we always go back to function 1 and we always go back to main. So C function calls are last in, first out. And if you wanted to have fun, you could, now's the time to work on assignments and assessments. And after the exam, if you want to have some fun, you could write a C program. How many function calls can you stack up? Can you stack up 10 function calls deep, 50 function calls deep? How would you do that? So C function calls are stack, but it's just one of many places we see stacks in computing. Right, so we're going to implement a stack in two ways, as a linked list or an array. But we without thinking about the implementation, we can actually talk about what happens with a stack. So we can think theoretically, without getting into what's happening and what the actual code is, what's happening with a stack. We can define operations. We can say there's an operation that creates a stack, takes no inputs, gives me a stack. We can say there's an operation to destroy a stack. We can say there's an operation to put one thing on top of the stack. This is pretty universally known as pushing to a stack. We can say there's an operation to remove one thing from a stack. That's called pop. and that would normally remove the item from the stack, and we can add perhaps an operation to count how many things are in the stack. So let's look at how we might code this up. How would we do this? How would we define the interface to all of this in C? And then how would we implement it? Well, let's have a look. New file. So what would be my interface to the stack? I'm going to type def a struct, and we'll call it stacked internals. I'm not going to say what's in there, and we'll call that, so that's a stack. So what did I say the operations were? I said create a stack, which is stack create, and it takes no input. So I give it nothing, and it gives me back a new stack with nothing in it. I'll put a comment to that in. Alright, so we need to have a corresponding I'm done with this function, which stack free, destroy a stack. So it returns nothing, but takes a stack as argument. There we go. Two functions in our interface. What else? What else? Oh, except I've got to spell stack with a capital S there. Push and pop, we said. So push takes a stack and puts an item on it. And here we hit a sort of a limitation in C that some of its descendant languages can get you around. Here we have to put it. We have to have what type of things on the stack. So we have to introduce a limitation. We're just going to have a stack of integers. Obviously, you can do. There's many possibilities here, but we're just going to have a stack of integers because we're interested in the notions of the abstract data type and manipulating it. But yes, it's a little unsatisfying that we have to say what type of stack it is here. And if you're going on in computing, yeah, look forward to addressing this sort of thing in complicated ways. Push, pop. Do I need anything else? Alright, maybe we want to say the stack size. Yeah, that's sort of useful to say the stack size. So I've designed 5 functions, without ever thinking about what goes on in here. That's it, and that's a beautiful thing. Now I can write equations. Not a bad thing here. You can sort of write formal equations to say what the results of these operations are without ever thinking about the internals. For example, if I push an item on the stack, I combine a push and a pop, the return result should be the item. Alright, that's one part of the equation, and this is my stack.h. Okay. Alright, so now we want to I want to show you how we'd call these functions first, and then we'll look at implementing. In fact, I'll show you how we'd call these functions, and then we'll take a break and look at implementing these functions. Stackdemo.c. So just example code that would call these functions. Stackdemo. Oh, what am I doing? We'll write it, and it'll include stack.h. Just a little bit of test code. So what we do? Well, the simplest test code we write would be something like this: stack s equals, what we call it? We called it stack free. Stack free. I called it stack free. So you see, there's my first two operations in place in a little function, little main that's going to use these functions. Creates a stack, stores a stack. What else do we want to do? We might push a few numbers onto the stack. And print out some things. So there's the outside view of our stack. Perform using a few of the operations, using create a stack, push 4 on, push 42 on, push 12, and then pop something, an item from the stack and print it out. That should print out 12, and this should print out 42. That's code to use the stack. This is the abstract data type. It's not well specified, so we really need to put more about the meaning of these operations in there. But if I added more statements about what the meaning is from of these operations, like for instance, the crucial thing here is it's the top of that would be the abstract data type, the interface, if you like, which I've implemented as in interface as a header file. Now what I need then is the concrete implementation. But we've been talking for an hour. Well, I've been talking for an hour. Hopefully you've been listening for an hour. I need a short break from talking. You need to stand up, refocus, whatever. So we're going to take a 5-minute break as soon as I've saved this as stackdemo.c. So let's take a break. If you've got questions, we'll come back to those after the break. And I'll talk to you then. All right, so 5-minute break from now. image. All right, everyone, welcome back. I hope you stretched, got up, and yeah, ready to think about this interesting ideas. So it's really nice that we're tackling this program top down. As coders, we often start bottom up. We've got a program to do, and we'll start. I'll do a scanf, and then I'll do this, and then I'll do a printf. So that's okay when it's a well-specified lab exercise that can be solved in one function, and it's 20 lines of code or something, or 10 lines of code. As we get to bigger and bigger tasks, that really doesn't work well. So here we've designed functions to provide this abstract data type. We haven't actually got to implementing these functions yet. We've even, I had a bit of work on this code over the break, and put slightly better code there that uses the functions supposedly for a deck of numbered cards. So it pushes 42 onto the stack, pushes 37 onto the stack, pushes 13 onto the stack, and then pops those off the stack. So that should print 42, 37, and 13. Okay. Now we can actually ask DCC to compile this, and we say, look, I don't have the other functions. The -c flag, I can't actually remember what C stands for, but it means I haven't got all the functions present. Compile what you see, and don't worry about not having the other functions present. It's stack demo, isn't it? So it'll compile stack demo and say, yep, that looks good, Andrew. That's all fine. You haven't done all the functions yet. So now let's go to the other side. On one side is calling these functions, using them. Here's our sort of definition of what the functions do. Can we implement them? Do a comprehensive implementation. Create a new file, which I'm going to call stack. And I'm going to do two versions. I'm going to do one with an array. I'm not sure we'll get to the array today. I'll do one with a linked list, and that's good, because let's just practice our linked list operations. So let's do stack linked list. Alright, so it's going to include stack.h. And it's going to implement all these functions. In fact, why don't I just grab these functions here, copy them over, just whack them in here. Bloop. How about that? And we just got to provide a body. Need a body here. Yep. Okay. What else do we need? There's one crucial thing I'm missing. Oh, what a stacked internals is. How are we going to implement this? I'm going to go with a pretty simple scheme. Just one field, which is a, what am I going to call it? A stack node, I guess. So our stack internal struct is just going to contain one field. Seems a bit silly to have a struct with just one field, but if you think about it, that lets us make this whole setup work. And that's just a pointer to the head of the list. And then we can say a struct stack node is a usual linked list thing. So what's a usual linked list thing? A next pointer. And the sort of thing we're storing in the stack, which is an int, what do we call it? Data. There we go. Yeah. Yeah, this, you're thinking, Andrew, I think I can get rid of that. Yeah, you can sort of optimize that away. Not necessarily a good thing to do, but that we want to use that struct for more things when we implement this with arrays. So we'll leave it that just like it is. Get rid of that space there. It doesn't affect the compiler. Will be happy with the space there. 0 spaces, 50 spaces, 1,000,000 spaces. DCC would be happy. It'd be a good thing to test, wouldn't it? You could torture test the compiler after the exams, put 1,000,000 spaces in a file and see if DCC goes, okay. It will. How would you do that? Well, you'd write a C program that outputted a C program which you put in the compiler. So you'd compile your C program, run it, which would produce a C compiler program which you'd compile. Can you then write a C program that, when you compile and run, outputs the same C program? Again, please, after the exam. Alright, creating a stack. This is, we've got, so we need a struct stack internals star s equals malloc. Alright, whenever we use malloc, we always call size of. Worried I'm not getting. Let me save this. Does it? Oh, there we get syntax highlighting. Yes, alright. For those of you who love syntax highlighting, I'm actually not a huge fan myself, but I know a lot of students are big fans of student syntax highlighting. Whenever we use malloc, we call the special operator size of, which says how big something is. So we can say how big is a struct in stack internals, how many bytes is that? It'll tell us, and we'll say to malloc, give us that many bytes. And what else are we going to do? Whenever we malloc a struct, we need to put initial values in the field. Up there, if you have a top 10 mistakes made by beginner C programmers, that would be somewhere about number 3, I think. Forgetting to initialize a struct created with malloc. We've only got one field in this struct, and we'll initialize it to null, because remember, if we have a linked list, an empty list is a null pointer, and then this can return s. Alright. Put code here to destroy the stack. I'm zipping along here. This is just great. Put an item on the stack. Alright. So we're given a field S and an item. Yeah, it occurs to me, by the way, I could have just said this is a stack, couldn't I? What's the type def? Let's go back and look at the type def. Struct stack internal star. Do I want to do that? Interesting question. Maybe not. I might leave it as it is. In this function, it's okay to expose the bare metal of our data structures. So these are we're inside. So I think that's probably better. To the outside world, we don't want the outside world seeing what's happening here. But in here, we're good. Alright. So we've got a pointer to this. How do we put something on the stack? It's the same way as usual. Stack node star new node equals, and create a new item for the linked list. Can be a bit tricky getting these exactly right. You've got to think about what I'm doing. I want memory space for one of these, a struct node, not a struct node star, a struct node. But I get back a pointer to it. So this is a struct stack node star. And now we have to initialize the fields. What are the fields of a stack node? The next pointer and the data. The data's easy. The data's coming in, it's the item. That's good. That we're putting on the stack. And the next node field will be the current head of the stack, current top of the stack. And the last thing I've got to do is change the stack head to be new node. So that inserts new node on top of the stack. Pretty good. Like it. How do we pop something from the stack? How do we remove the first item from the front of the list? That's what we want to return. How about that? That returns the top of the stack. Right. All right, we haven't implemented this function yet, but for now, if I can get this into insert mode, let's put it. To make this compile, we'll just say the stack always has 42 things in it. So we haven't implemented that function. Should be familiar with it. You start off assignment 2 and you've got this pile of functions to implement and you steadily fill them in and complete them in. Alright, so this one not implemented yet. But I think I've implemented the other functions. I've set up a complicated data structure where I have one struct that just remembers a pointer to the first item in a linked list. I've got a struct for a linked list of items. Each one, so this will have a pointer to the first item on the stack, it'll have a pointer to the node for it, it'll have a pointer to the second item on the stack, and so on, the chain. So we'll always just have one of these, and we'll have 0 to many of these ones, all linked together by pointers, with the magic of pointers. Not magic, with the wonder of pointers, that's a better word, the wonder of pointers. We're creating a stack here, and every time we put something on the stack, we do it. Now I can spot 3 things I think missing in this code, but I think it might compile. So it's not bad. It's always good to compile as early as we can. You saw me compile just stack demo.c to see if that all made sense, even though we only didn't have half the functions done at all. I now have definitions for all the functions, In this case, the definition is just a stupid thing that doesn't really do what the function's supposed to, but it'll let me compile. So I'm hoping I can say, here's a linked list, a concrete implementation of this abstract data type combined with code that uses this, and our DCC will say, that's a good program, Andrew. You wish. Alright, line 5 I've forgotten the semicolon. Line 10 I've forgotten the semicolon. Yes, I'm not entirely sure why struct definitions have semicolons after them. Oh, implicit definition of malloc, because I'm DCC saying to me, Andrew, you're calling malloc but you didn't hash include stdlib.h. Alright, there's more errors there, but honestly, fix 1 or 2 errors. Don't bother about the rest. Recompile, see what the errors are now. Alright, it's saying this data has, oh, yes, I'm a bit confused, aren't I? This is I can replace this with the can't I? That's what it is. And does a struct stack internals? It has a head field only, and I'm trying to use this. What I really meant was get the first item in the list and then return its data field. And I've misspelled that. I think I've got a working program now. Well, something. Let's compile it. Let's put it in a file we can run. See how we go. Alright. Does it correctly implement the operations here? Will it push 42, 37 and 13 onto the stack and then pop them off in reverse order? Oops. If I typed it. Oh, pushing 42 on, pushing 37 on, pushing 13 on, taking 13 off. So far so good. But then it got after we removed 13, we should see 37 and then 42. So you could actually write this as test functions, couldn't you? You could actually say, check that this matches this, check that this matches this. This could be a little test routine that made up 10 random numbers, pushed them on the stack, popped them off, checked that it worked. What a good idea. Which I won't follow up on now, but why isn't my code working? Because my stack pop returned the top item of the stack, so it returned it did the return bit, it didn't do the remove bit. What was I thinking? Alright, I'm on this. There we go. That will remove the top item on the stack. Make the head field point to the next field of the head item. The top item is gone. Excellent. Oh, come on. I fixed that. But I didn't save it. Come on. Look at that. Stack in, stack out. Amazing. Push, push, push. Pop, pop, pop. 42, 37, added to the stack. That's check it out. Let's put put 4 things on the stack and pop 3 things off. Yep, look at that. Push 42, 37, 13, 678 on the stack, and then first thing off the stack is 678, next thing off the stack is 13, next thing is 37. Oh, it's not a very good card number, is it? Yeah, it doesn't really fit our metaphor of cards. We'll make it 55. No, that's, well, it could be a bigger deck. 23, there we go. Alright, yeah, can we spot any weaknesses in the code? You probably have. You probably spotted there's a couple of weaknesses, there's a couple of things wrong with this code. Alright, yeah. So, one of the things I've said to you is whenever you use a pointer, e.g. with an arrow, you have to ask yourself, how do I know that's valid? How do I know it's not null? Do I know here that when I use sHead that it's not null? Can sHead be null? When is sHead null? It's null when the stack is empty. So that seems, line 37 and 36 there seem unsafe to me. They seem like they could break. Can we actually see them break? What happens if up here I call stack pop straight away on an empty stack? What does that do? DCC says, Andrew, you're using sHead and it's null. You're trying to get sHead arrow data and it's null. Really looks like something we should be checking for, doesn't it? It actually gets you an awkward thing. What do we return if we get null? What do we do? That's a design decision. I'll show you one design choice. One design choice is to terminate the program. So we might print an error message. You can come up with a better error message. Let's be error, all in caps. Now, if we want to terminate the whole program, there's just nothing further we can do. I'm not sure we even cover the exit function. Has that come up? That's hard to say. Exit is a special function that just stops the whole program. So, and you can give it a number to say whether things are good or bad. 0 by convention means things are good. A positive number means things are bad. Come back in COMP1511 and that will just get, well, and come back in later courses, we'll explain much more about that. But a program has a way of saying, did things go well or not? And it's a number. 0 by convention means, yeah, everything's okay. Every other number means, no, there was some sort of problem. So we're going to say, this says stop the whole program there, don't return. And print out a message. We've done a lot of coding where we're just writing main. And you don't need to use exit in main because you can stop the whole program in main just by returning. But the trouble is, we're several levels down the function call stack here. If stack pop returns, whatever called it keeps executing. So it doesn't. It either has to do. You have to make a design decision here. Either it can return a special value to say things went wrong, or it can just say, oh, I'm not going on. And this is not necessarily the best design decision by far. Now, a few of you have seen a lot of Python, and you're thinking, wouldn't exceptions be a better way to handle this? Oh, yes. So that's something that's missing from C, is a principled way, a part of the language for handling when things go wrong. And in Python, it's called exceptions. And those of you who've done it, who are really spent a year or two playing with Python, might have played with them. Don't worry if you haven't. We have courses for that. Or you can teach yourself Python after the exam. All right, not a bad thing to be doing at all, by the way, particularly in lockdown. All right. Pop of empty stack. I think that's fixed the problem. I think that will get an error message and an exit. Assuming I put a semicolon on that. And I'm not actually sure. Can't remember which include file specifies exit. Printf. Minutes today.h for printf. Hey. And there we go. There's our error message. Now you're saying, well, is that much better than what we had before with DCC stopping with a runtime error? It's a bit better than that, but the other thing to remember is DCC is a very special C implementation we have for working with as a beginner programmer. A lot of C isn't compiled with the checks in DCC. DCC actually runs a lot slower than because of these checks, and so we don't always turn these checks on. Definitely don't always turn these checks on. So it's better if we do our own checking. All right. Rather than depend on DCC and DCC just giving this generic message about a null pointer. I think that's otherwise correct. There's another problem here. There's a major problem here, which is leak checking. So let's look at that. We might not get to arrays. I'm going a bit slowly here. Don't panic. We'll finish with implementing this with arrays on Thursdays if we have to. Leak checking. Am I freeing up all the memory I'm allocating? Do I have a memory leak? Or is every malloc somewhere, every piece of memory allocated with a malloc freed up? I guess there's one way to find out, and that's to add a leak check flag to DCC. And I'm betting it's going to say memory error free not call for memory allocated with malloc in stack create in stack linked list at line 17. That's a bit sad. Oh, I'm not calling stack destroy here. Well, that's easily fixed then. So the memory leak, the problem is not in the implementation. The problem is in stack demo. It's part of my. There really should be a message here, shouldn't it? And that's a classic message to put. You must call stack free. Something like that. So you've got to warn the person using your functions. If you call stack create, you've got to call stack free. So I'll put the warning in. I'll put the call. So the last thing is I'm going to say, oh, look, I'm done with the deck of cards. Here. Bloop. Go. Alright. Oh. Free not call for memory allocated with malloc in stack push. That's a bit weird. So it's a different error. It's now saying, before it was saying you allocated the memory in stack create and on line 17. Now it's saying, oh, look, you allocated memory in line 29 and it's not freed up. Let's look at my code. See, this is a nice example of a memory leak. Alright. So it's saying, look, yeah, line 29, you call malloc there, but you never call free for that. Where am I calling free? When I allocate abstract internals there, I free that there. Not using free anywhere else. Oh, I spotted the problem. Look down here in stack pop. I remove an item from the top from the linked list, but I never free up the space. And I've got this. Now my first thought would be something like this. No, that doesn't work because I've just changed. I've got this dilemma. We've seen this before. I can't do this because I need to use the next field of the pointer of the first item in the list, and I need to free it. So I need another variable. If I compile and run that, well, we'll compile and run that. We'll get a runtime error. Because I've freed up the first item in the list, but then I look at its next field. You can't use memory, you can't look at memory after you've said it's free. That's very, very dangerous. But there's a way out, isn't there? Restruct stack node star. Something like that. Section. I'm using shead a lot there, isn't it? It'd be better if I said struct stack node star. Something like that, maybe. Yeah, that's looking better, isn't it? Spell properly. There we go. Beautiful code. Guaranteed to work and solve my problems. Can't possibly have any bugs. Well, missing semicolon doesn't count as a bug. Nor does an extra equals. This time for sure. Alright, I've freed up my memory. Run it. Oh. Still telling me free not call for memory allocated with malloc. Why doesn't this work? I'm freeing it. And this, yeah, this is a hard. These sort of problems get quite hard. You got to think quite cleverly about this. So, what's my data look like? It's a struct stacked internal, and it links off to a series of stack nodes, and there could be one, there could be, well, it could be 0, 1, 50. And when I call push, I malloc a new one and put it on the front of the list. When I call pop, I remove the one from the front of the list and free either. There is a problem. What happens if we get to the finish and there's still items in the list? Yeah, that's a bit tricky. debugging with this is a bit tricky, but we could say we could print out what S head is here and see if there are items in the list when we're exiting. So let's put a bit of debugging code there and print out what the head of the list is when we free it up. And we'll spell printf properly, actually with an F. Oh, alright. That's the pointer. It doesn't tell us a lot. It tells us really one thing. It's not null. So there's something in the list. Yeah. So what those exact numbers mean, who knows? But it's not null. It'd be all zeros if it was null. So we've got to free up the list. Oh wait, but wait, I have code to do this already. Don't I have code to do this? Free players. I do. Different types, but let's see if I can make it work. So instead of a struct player, it's a struct stack node. And it starts at S head. That goes down the list of remaining items in the stack and frees them. Whoa. That's a complicated example. And now we're freeing up all the memory we allocate. That's a really, yeah, this is sort of the, I'd say, apogee height of stuff we cover in COMP1511. This is a complicated example, getting across many things. So definitely it's very okay if it's going to take you a lot of thinking to understand everything we've covered through there. But that's a linked list implementation of a stacked abstract data type. So we're saying this. What can you do with a stack? You can create it. You can destroy it. You can push something onto it. You can pop the last item. So you can add an item to the stack. You can get the last item from the stack. Notice you can only get the last item from the stack. There's no way to say give me the third item or what's the 27th item. We only have access to the top item, and we haven't actually implemented that function. You can do that as an exercise. Tell me how many things are in the stack. So there is abstractly what a stack is. Here is concretely done with linked lists. Some easy code, some hard code is linked lists. Is a concrete implementation doing that. And last is something using this implementation, but could use any implementation. So this test code it doesn't care how a stack is implemented. It just wants push to work, pop to work, stack create to work, stack free to work. It just wants a stack. It doesn't care how a stack works, what's inside a stack. And this is all it can see. It can't see what we're doing behind the scenes, and that's enormously useful because now this manages the complexity. Narrowing this interface means we can produce systems that are more robust, and we can build systems easier, test systems easier. The only thing we have to worry about now for the correctness of our stack linked list is, does it perform these operations? Sorry, does it perform these operations correctly? All right. Don't worry too much. These are all just concepts being introduced, which if you do more computing courses, you'll see much more of. All right. Now, could I do this as arrays? Could I change this and do it all as arrays. You're saying, can I do a different concrete implementation of this? Alright, so rather than stack linked list, have behind the scenes an array. And it's a nice way to compare a couple of things. One, to show us two concrete implementations of a single abstract data type. The other thing that's nice is to see strengths and weaknesses of linked lists. I've got a job to do. Should I be choosing linked list? Should I be choosing array? So we'll have a stack done with an array. Create that. Yeah, most of this code's got to go. Well, let's start with the stop. Alright, first thing to go, no more linked list nodes. Up here, we're just going to have an array. So we might have stack data. I don't know where I just typed that. I'm a bit worried about where I just typed that. Oh no. There we go. So we'll just have an int array, stack data. Arrays have to have sizes, and that's the big thing we'll see here. Our linked list implementation, there was no fixed limit there. You could push 5 things onto the stack, you could push 5 million things onto the stack. On this computer you could push 5 billion things onto the stack, and that would all work fine. You could do 5 billion pushes, 5 billion pops. It'd take a few seconds, but it would work. Here we've got to put a fixed limit in. That always worries us. It's always a weakness we're introducing. So I've said most things that can be on the stack is 1024. We also have to remember where we're up to on the stack. So how many things are in the array currently? So we've got an array that can hold where we put 1, 2, 3 more, and we'll have an index into the array saying where the last thing put on the stack was. Arrays implementation, then initialization. We actually don't have to initialize the array because it starts off with nothing. We have to initialize the top field to say there are 0 things in the array. Destroying the stack just becomes easier. We just have to, we've got a single struct here, so we just free it. Putting an item on the stack actually becomes easier as well, except we need another test. Let's first do what we put on this. We can put an item on the stack by just saying stop++. And we call it stack data. Oh, we've got an interesting question. stop points 1 above the, I guess, what's on the stack. Yeah, that's an interesting thought, isn't it? It's crucial here, isn't it? What that is. So it's how many items on stack. Let's quickly do pop as well. Top data equals Huh. That's pretty good. Actually, no. I've deleted code we need. We don't need that, but we still have a special case, don't we? Same special case. It can be good to implement something two ways. It's pretty common when you're developing to actually implement something two ways. Often you'll do a prototype. You might quickly do a prototype in, say, Python, and then do a full C++ implementation in real coding. Or you might quickly use a simple data structure to mock things up, which is not going to work on your database of 100 million users. But you might use a simple data structure behind the ADT. Get things working, and then put a more powerful data structure behind it that can cope efficiently with 100 million users. So we've got to check if there's nothing in the stack. Do the same thing again. If there's no items in the stack. Otherwise, then we shrink one, and what we want to return then is actually that should be correct. Alright, I think that's almost correct. There's a test missing from this, but I think that will work for our code if I've coded it properly. Put an array inside the struct. Keep a counter of how many items on the stack. Set the counter to 0 when we create the struct. We don't have to initialize the array. We've only got one struct, so we can just free it up. To add an item, we store it in the count. Use the count field as an index. Store it there. Think about that. Will work. Add one to the count. If we're asked to pop one and there's nothing in the stack, print an error. Otherwise, reduce the counter by 1 and return whatever's at that index. Think about that. You draw that out. That should work. I'm pretty confident in my code here. Alright, so I'm going to try. Watch this. And it gets. Well, actually, now let's check it out. Let's compile it in isolation. Say, just check out stack array for me, DCC. Tell me that looks okay. It does. Alright. Alright, fingers crossed then. I'm going to say, alright, instead of using the linked list concrete implementation of my stack abstract data type, use my arrays concrete implementation of my stack data type. Call it from, you do some calls from stack demo. We'll run it and see how and it should do the same thing. Fingers crossed, we're going to see the same output slotting in arrays behind the scene, and there we go. So this one linked lists, this one arrays, all hiding behind same stack.h. This didn't change. This code doesn't change. This doesn't know whether there's linked list or arrays behind the scenes, because this doesn't say whether there's linked list or arrays behind the scenes. This is the arrays implementation, and we saw the linked list implementation. Alright, there's one key thing I wanted to show you for it was in our last seconds, and that's the big limitation of arrays. We're missing an if statement here, because we could overflow the array here. Every time you use an array index, ask yourself, how do I know that's within bounds? How do I know that? And I don't. There's no way to know. This array is of a fixed size. Its maximum size is 1024. So we've got to check here and do a check like this. Aha. Here we go. Stack Overflow. Nice error message. All right. So that's embedding that limitation. I'm not going to write code to put 1024 things on the stack, but we would normally write test code for that. All right, I'm going to ask Tom, who's with us today, if there's any key questions in the chat. A big thank you to Luca, who's been answering questions busily in the chat. Thank you to the Oh, sorry.
Oh, sorry. Nothing key. Any outstanding questions really? But I'd reiterate what you said there, Andrew, which is with ADTs, it's often super helpful to think about how you're going to use them before you implement them. And actually the same goes for functions as well, in my personal experience.
You think about this, what functions you're going to do, and then you might actually sketch out an example code like this well, that doesn't have to be in your head. Definitely doesn't have to be in your head. Before you launch into I'll do all of this stuff. This should be last. Yeah. So excellent point. Thank you, Tom. All right. So I have sadly a Teams notification for my next meeting. I hope you have a more exciting day than me. Can do things like focus on Pokemon and Pokedexes or the lab exercises. So thank you for all of you who have joined us from 9 o'clock on a Tuesday morning. I'll see you at the more sociable hour of 2 o'clock on Thursday. Well, we might recap this, but then we're going to talk about recursion, which is a really beautiful topic. All right, so see you all then.